Welcome to PicoGenius.com, where science, electronics, and microcontrollers converge. In this two-part series, we'll be looking at the Pico Pi being used as a data acquisition device with National Instruments LabView application. LabView is a software platform developed by National Instruments for data acquisition, instrument control, and industrial automation. LabView is a graphical programming language that allows you to create virtual instruments, automate tests, and control industrial processes. With LabView, you can easily design user interfaces, analyze data, and interact with hardware devices. LabView is widely used in research and development, in academia, and in industry, particularly in the fields of physics, engineering, and biomedical research. The software is highly versatile and can be used for a wide range of applications, from measuring signals in a laboratory experiment to controlling complex manufacturing processes in a factory. Raspberry's Pico Pi is a microcontroller board developed by Raspberry Pi Foundation, which was released in January of 2021, and is designed to be an affordable, easy-to-use platform for electronics projects and learning. The Pico is a single-board computer based on the RP2040 microcontroller chip, and it has a dual-core ARM Cortex processor running at 133 megahertz. It has 264 kilobyte of RAM, 2 megabyte of flash memory, and 26 multifunction general-purpose I/O pins. In addition, it has 2 UARTs, 2 I2C controllers, 2 SPI controllers, and 8 programmable I/O state machines. Also, the Pico has a built-in programmable LED, a 3.3 volt 12-bit analog digital converter, 3 hardware pulse width modulation channels, a built-in real-time clock, and a built-in temperature sensor, which we'll be using in this project. Pico can be programmed using a variety of programming languages, including MicroPython, C and C++, and CircuitPython. It also supports a range of development tools, including the Raspberry Pi C, C++ software development kit, and the Thonny Python IDE. To get started, we'll look at the block diagram for this project. Simply, it's a Pico Pi, which is set up to input a potentiometer, which has been configured for ratiometric readings, meaning it reads the voltage from ground to the supply voltage, which in this case is going to be 3.3 volts. We're going to input one switch as essentially an event, and so pressing the switch will put a logic 1 on the input pin on the microcontroller. In addition, we're going to use the internal temperature sensor in the Pico Pi as a source of data. We're going to collect all 3 of these, we're going to process them, and then we're going to send them to a 16 by 2 LCD display. Schematic for that for this application is right here. So put simply, the push button is connected to GPIO pin 12. It is pulled down internally, which means that when I close the switch, a 3.3 volt signal will be applied to GPIO 12 as a logic 1. Secondly, we're going to have a potentiometer that's going to have one end connected to ground, the other end connected to the supply voltage. And the wiper of this pot will be able to swing all the way from ground to the 3.3 volts. That value will then be read by an analog digital converter on GPIO 28. The internal temperature sensor is in the chip on the Raspberry Pi, and it will also be used as a source of data. Once these three devices are read and some software processes them, they will be sent over the I2C bus to a LCD display. What this looks like in real life is the Pico Pi on a breadboard with the LCD. You can see the I2C lines connected to the Pico. Potentiometer connected to the GPIO pins, and the switch connected to GPIO pin. So the hardware is pretty simple to set up. We'll take a look at the software. There's not a lot to the software, but let's take a look at it. So this is a MicroPython program. This program is designed to read values from three input devices: the temperature sensor, the potentiometer, and the push button. It then processes the values and displays them on the 16:2 LCD screen. First three lines of the program set up the necessary connections in the libraries. The machine library provides access to hardware on the Pi, including the analog to digital converter and the general purpose I/O pins. The I2C library provides an interface for communicating with the LCD display over the I2C bus. Next few lines on the program here they set up the connections to the three input devices and the LCD display. The temperature sensor is internally connected to an ADC, analog digital converter, on pin 4. The potentiometer is connected to an analog digital converter on GPIO 28, pin 28, and the push button is connected to a GPIO pin 12 with the input pulled down, as you can see in the code here. The I2C address variable is set to the address of the first device found on the I2C bus. In this case, there's only one device, and that's the one that it finds, and it's the one it's going to use. This will later be used to communicate with the LCD display. The temperature C function that you see in the def statement here takes raw data from the temperature sensor and converts it to a Celsius temperature value. It does this by first converting the raw value to a voltage, and then using a formula to convert the voltage to a temperature. This will be called by the main loop to get the temperature readings from the Pico Pi. The while true loop, is where the program continuously reads the input values and displays them on the LCD. Inside the loop, the temperature C function is called to get the current temperature in Celsius. Even though I don't use it, the Celsius value is converted to Fahrenheit and equated to the variable temp F. The value of the potentiometer is read and scaled between 0 and 50. If the value is less than or equal to 1, it's set to 1 to ensure that the values from the potentiometer are always positive. The value of the push button is read and stored in the button variable. If the button is not pressed, the value is 10. If the button is pressed, the value is 20. That's arbitrary. I just gave it two values so that we could see that the button is pressed or not while the software is running. The last lines in this program are used to update the LCD screen with current values of temperature, potentiometer, and the button. The sleep 1 function pauses the program for 1 second before continuing to the next iteration of the loop. Finally, the LCD is cleared before the next iteration. So, as you can see, the hardware and the software for this project are not too bad. There are a couple of details that I need to make you aware of to make this program run. In particular, there are 2 external libraries that have to be placed in the root directory of the Pico Pi in order for the software to run. Those libraries are, the first one is Pico _I2C _LCD .py, and the second library that needs to be in your root directory is LCD _API.py. I got these libraries from Tom at Tom's Hardware at the URL shown on your screen. This page that Tom has created is all about interfacing the Pico Pi to the 2x16 LCD display. Drop by and check out his tutorial on that. These 2 libraries and this presentation and the program and the schematics, everything associated with this project can be gotten at PicoGenius, www.picogenius.com. Just go to that page. There will be a link to this project, and in that link you will be able to download everything you need to perform this project. What we're going to do next is we are going to take a look at a demonstration of the program working and the hardware working, and then we will close this portion of this project, and in part 2 I'll set up a UART on the Pico Pi, and we will send these values to a PC that's running the LabView application. So this is a demonstration of the circuit in operation. This is the potentiometer. You'll notice the pot value is now 1. As I turn the pot clockwise, the value of the pot goes up and goes to 50. So it has a range of 1 to 50 through the entire rotational range of the potentiometer. Temperature sensor is at about 31 degrees C. If I heat that up, let's see if I can heat it up with my finger. Notice it's gone to 32, 33. If I had something a little hotter, there it is at 34. So the temperature sensor on the chip itself is heating up and displaying. The button press, you'll notice that it's at 10 right now. When I push the button, the value goes to 20. Okay, this is the operation of the circuit. In part 2, we will transfer these values through a UART to the PC and display them on the LabView virtual instruments.